much just to so everyone is aware, we're recording this. This is our IAMOT talks. For those who don't know me, my name is Breno Nunes. I'm the president of IAMOT, and I sit here in Aston Business School as reader of Sustainable Operations Management. Uh, well, for those in the US, that's probably equivalent of associate professor. So we have different terminology, different for the academic jobs in the different countries. But it's great to see many of you here, many of you that I have already met, and nice to meet you to those I haven't yet. Um, my job here today, it's actually quite simple. It's just to introduce Professor Massoud Amin, who kindly agreed to deliver this talk. 27 years of smart grid development and investment key insights. Before I do that, I will just remind you of our IAMOT conference 2025. So there's still time for you to submit papers. You can submit actually an extended abstract, a short paper, or a long paper. Also, make sure that you invite your PhD students also to submit proposals to the PhD colloquium. So it would be really good. I think it's one of the most popular parts of our conference, of our annual conference, is the doctoral colloquium. A lot of people get, the doctoral students get a lot of value out of it. But I think let's go to the important part of this now, because I've known Massoud for many, many years, and I put this in record what I have already said in private. I'm a great admirer of Massoud's work. I've been inspired by his talks in IAMOT, and I will not make the mistake of introducing him completely here, because I know that I'm going to miss a lot of interesting stories that just himself can talk about. But I can tell you that Massoud was born in Tabriz, capital of Iranian Azerbaijan, and he went on to graduate in engineering, and went in through a great career, which culminates with professorship in various universities. But now he's emeritus at Minnesota, University of Minnesota. Important to say that I've met Amin through IAMOT, and we were very honored that Massoud was actually the president of IAMOT for a period of time, and has always also been very, very supported in our board of directors, providing valuable insights on the direction of the association and contributing in various conferences as keynote speaker. So I think that I will stop there, because I want this to be, of course, a talk, but that we move into a conversation, and then we learn not just the great work that Massoud has done subject-wise, but also about his career and how he managed to convey so many people to tackle world challenges that now perhaps are even more important to be tackled now, with the challenge that we're having. So Massoud, over to you. You can share your screen.
Good morning. Thank you, or good afternoon, depending where you are. Thank you, Professor Nunes, for the kind introduction. It is an honor for me to be here and to meet all of you. Many of you I already have met, have had the privilege of working with. So it's truly great to come home to IAMOT, and I'm at your service. So I'm really delighted to share this, because 27 years ago in January, I introduced the whole, not just concept, but a proposal to fund this work when I was head of mathematics and information sciences at Electric Power Research Institute at EPRI, and presented it to the Research and Development Advisory Board at EPRI in Palo Alto, because we were concerned about Y2K, aging infrastructure, deregulation, different factors. And our concern was or question was, can we improve efficiency and all these different factors that are coming in without diminishing reliability of the entire grid, and also in different regions, because different regions are hit by different things. Physical attack was a concern also. There was about 2% of all the major outages were caused by human error or other human either error, or in some cases in Colombia, in Israel, elsewhere, attacks on the generation or substations. So with that as background, let's begin. If you think about it, have you ever been in a city during a blackout, like New York City or any other city? How about, have you ever been in a village without electricity? What's the quality of life? Reliable electricity, and electricity being the most efficient carrier of energy, much more efficient than compressed air, hydrogen, and other sources. Access to reliable, affordable electricity underpins GDP growth of nations. Question is how they use it. And that, of course, we cover in IAMOT. How do we create clusters of innovation? What vectors of innovation we focus on? And I won't get into it. But if you think about how critical this foundational infrastructure is, it really underpins our economy, our quality of life, our security, and everything we do. And we often take it for granted. At the turn of this century, in 2000, there was a Blue Ribbon Commission at the US National Academy of Engineering, led by Neil Armstrong, to assess and rank the 20 greatest achievements of engineering in the 20th century. I thought, oh, it's obvious, it's a done deal. Neil Armstrong, I remember watching him on a black and white Grundig TV when he walked on the moon. This man going to the moon. However, the commission had a lot more wisdom. They chose the North American grid as the most critical and the greatest achievement of the 20th century, because without that, we could have never gone to the moon. We could have never done many things in technological advancements that we have done, or economic development, or nearly doubling the human life. Clean water is because we have electricity. And modern medicine is enabled by power and electricity. So it's no surprise that electric power and communication infrastructure are deemed to be the most critical among the what Department of Homeland Security in the US ranks as the most critical infrastructures in our nation. So if for a second you close your eyes, you take a deep breath, and you think about... I'm sorry, did somebody have a question? I'm hearing a background noise. Okay.
Can I just politely ask, if you do not have a question, to make sure that your microphones are closed, please? Thank you. Massoud, you're muted now.
Thank you. So if you, for just less than a minute, you close your eyes, you take a deep breath. Don't look at the Venn diagram, but think of do national security, environmental security, and economic security intersect? And if they intersect, what's at their nexus? What's at their intersection? I submit to you that energy security is at the core of all three. And there are no single silver bullets, but there are many innovation bullets, and hence role for IAMOT to work even more so in this area among many areas that we work. And to put this in perspective, in the US, we built a Cadillac for the 20th century. As the Blue Ribbon Commission assessed, yes, we built a fantastic networks in the US and in North America with Canada, but that is a relic of a 20th century. And the question is, will it remain and become a relic of the last century, or is it going to become the underpinning infrastructure for the 21st century digital economy that we are going through right now? And these are some of the data on what's going on to bring you up to date. About 75% or 74% of the transmission lines are old, or 25 years or older. They have a life expectancy of about 40 years, but many nations, we push it beyond that. Cost of outages, everything else, cyber threats. We had 42% increase in 2023. We had 70% increase in cyber attacks on the power grid in 2024. Data just came out last month. And we look at it often in a silo. We don't think about the whole system. If you think about this in a silo and do innovation, that's great. Power electronics, transmission and distribution or generation. But what we do, which connects to also IAMOT, we do system end to end from fuel source through the supply chain, through generation, transmission, which is high voltage, 100 kV and higher, sub-transmission 30 kV to 100 kV, which usually we kind of cluster it with, we just call the whole thing the grid in the more recent decades, and then distribution closer to the customers, 15,000, 15 kV and lower, closer to the customers, and then the end use. Like a Russian nested doll, the most important part is human beings. We try to provide services, quality of life, to human beings and to society. If you look at how we got here in the last roughly 120 years, initially with hydro dams, we had, in upstate New York, transition to coal, transition to oil, nuclear kicked in, and the natural gas kicked in, and more wind and solar. So what did it do? The generation that was added and subsequent transmission lines to bring it from where the sources were available to population clusters, as India does, China does, Brazil and other nations do, is build the generation away from population centers and build transmission, high voltage transmission, and bring it to cities and byways kind of along the way. And then we had rural electrification also. It provided support, economic support, life support, quality of life, initially to about the population that you see on the chart. But as the population increased, we ramped it up. So where are we today? Here is a summary. I'm not going to go through every bullet. My slides will be
Good.
all available to you.
Sorry,
Hello?
sorry to interrupt. Sorry to interrupt. You're not sharing your slides, so if you
Sorry,
want to
did it
show
go
something,
down?
no, I think it stopped at some point.
Allow me to troubleshoot. Oh,
Yeah.
yeah, it says I'm sharing.
Oh, I mean, is anyone seeing these slides? Because it's not showing on my screen, I'm afraid.
No, we can't see it.
I wonder what's going on. I have to leave and re-enter again.
Well,
Yeah.
if you want to send it to me, I can share on my end if you want. I mean,
I'm
it's up to
sorry,
you.
it's too big, and by the time
Okay.
I turn it into PDF and email it to you, it's going to be the end of the meeting. So
Just
I
try.
think it's a problem probably with the connection, but I'm good. It's showing, actually, it doesn't allow me to, it says share is already grayed out, and it says meeting organizers and
Okay,
presenters can
okay.
share.
So I'm putting you as a presenter again. You should be able to do it now.
Now, okay, now it says share. Good, good, good. Sir, I think when we went off with the person who talked in the background,
Yeah,
something happened. Yeah, okay.
it's all right.
Okay, so thank you. Technology, we talk about technological leadership and IAMOT, and still Massoud Amin, as the former director of Technological Leadership Institute, head of MOT at the University of Minnesota, has problems with technology, tech support. So I'm not going to bother you. I don't know if you saw this transition or not. If not, you saw this one, right? Hello, can anybody hear me?
Yeah,
Yeah, I
definitely.
don't, and I don't think we saw any of that, Massoud.
Ah, shoot. Okay, I'm not gonna, I don't wanna take too much of your time, but unfortunately the technology glitch. So this is the part I talked about, the whole end-to-end system and dependencies, interdependencies with supply chains, fuel supply and everything. This was how we built the whole system, the part that I talked about it already. So since we are recording, I won't repeat it again. We will just how we increase, we ramped up generation and transmission to keep up with demand and with population growth. Then here is the part about current state, getting a pulse check and neuron check, as some call it, where we are currently. The increase is mostly because of electrification, data centers, and transportation, which is electrifying. And this is giving you some of the data of what are going on. An aging infrastructure, what we have to retire, there's no choice. And then what are the actions we need, especially for economic growth, environmental security, and national security. They are on the right-hand side of your screen. Again, my slides will be available to you. I will turn this into a PDF and email it to Professor Nunes. Now, a question about efficiency. Please look at the far and take a pencil or a pen and a piece of paper. Don't look at my numbers. Coal is about 35% efficient, meaning that when we burn coal and turn it into steam and run it through turbines, we get 35% efficiency. Transmission by itself is about 97% efficient. That's why it makes more sense to have them away population centers and have it from, whether it comes from Brazil, from the Amazon, or in China or India, bring it, or from Niagara Falls, or nuclear plants, etc., from far away to population centers, about 97%. And the more we load it, it gets, lines get heated, they can even get damaged, as we saw in Australia, other parts of the world. Distribution system, lower voltage, is less efficient. And also, if you have economic theft, when you travel internationally, you see all those lines like a bowl of spaghetti near a local tower. Usually it's theft, that people have either wired it themselves. So we can get as low as 50% efficiency. You know, before we had smart meters, interestingly, I will go to that question I was going to ask you. So when you combine transmission and distribution, it's safe to say it's about 97% efficient. Lighting, incandescent light, what came out of Thomas Edison's lab, is about 3 to 5% efficient. Of course, if you put LED, that's about 10 to 12 times more efficient than that. If you multiply 0.35, which is the efficiency of the coal, and if you put carbon capture on it, you need energy to capture carbon, goes down to about 25 to 27% efficiency. But let's say for now, just multiply end to end, 0.35 times 0.9 times 0.05. What do we get? We get 1.6% efficiency. We are wasting over 98% of energy content in that coal. Does it even make sense to do it anymore? The other factor is cost and impact of outages have been rising. Here I'm showing you the very first benchmark that I had the privilege of being part of. We did on the left-hand side. Two types. One is actual blackout, power outages, and the other part in maroon is power quality, the kind of almost disturbance-free electricity we need for all the electronics, silicon-based chips, and other devices. That's the cost to our US economy, just in the US. Department of Energy and others have done same assessment, White House, and I had the privilege of supporting the White House way back. Minimum for outages is 38 billion a year in economic losses to over 150, 170 billion. And these outages have been increasing. I share with you on the right-hand side of the screen my own assessments of what I have done and peer-reviewed, etc. Some of it will appear in my book with what can we do from a leadership management of technology viewpoint. It's called book is on technological leadership. IEEE and Wiley will publish it this summer. So another factor is security. And if you recall what Ukraine went through just before Christmas in December of 2015 and 2016, two cyber attacks on Kiev, on also on Ukraine. And these are showing you those cyber attacks, how much of electricity they actually took out. And the name of the attack, Black Energy 3, took out about half of the utilities in Kiev, 3 out of 6. And it's a very targeted, almost like a specific weapon, built malware to go to take out the electric grid components. In summary, the power grid is aging, is facing challenges from climate risk. We need climate resilience, cyber threat, physical attack. And I didn't get into physical attacks, but if you look at rifle shots, high power, some of it by people who don't know what they are doing, but some targeted. What happened in the Bay Area, that they took 16 high voltage transmission transformers, high voltage transformers in California. And if they had taken 2 more, we would have had major blackout for long term, because we don't build or manufacture such things in high volume. We don't have stockpiles, and it takes 1 year to 2 years to build, deliver, and fit those. But they knew what they were doing, and the assault that took place was very, very smart, stealth, use the bushes to hide themselves, and they drain the oil in the transformers. I won't get into it. You can look online for different areas. The good news is, my apologies, investments have increased. But of course, we talk about that. We still need to do more targeted end-to-end look at where the biggest sources are, top 5 areas, and go deep into them and augment them to enhance security, resilience, reliability of that system and the entire network. But from an investment point of view, short-term renewable gains with long-term resilience, mainly because, as you saw, these storms, we used to have 2 to 5 storms that affected 100 megawatts or higher, 100 kV and higher, and in terms of outages, 100 megawatts and higher from 1950s, 60s, 70s, 80s. In mid-1990s, something happened. Number of outages rose from 2 to 5, 3 to 5 to over 70. Now there are 134 such outages just in North America. So annual cost, is safe to say that the median is about 150 billion. Global is rising. The number is not really 75 to 180, 150. It really depends how much we electrify. Depends a lot on also on China, on India, sub-Saharan Africa, and we still have about 640 million people in mostly in sub-Saharan Africa with no electricity, and about 3.7 billion who have 4 hours or more blackouts every day. So what do we do about it? Here is what I propose, what I've had the privilege of working on for about 27 years, building on the previous 15 years of experience I had from C4I systems and damage resilient combat systems for helicopters, for aircraft, F-15s and others, and logistic networks for Air Mobility Command, Transportation Command for the US Department of Defense. So I joined EPRI in Palo Alto in January of 1998. Before that, some foundational technologies that already existed, I'm showing to you on the far left-hand side. Basically, almost like the Lego pieces, how do you connect different modules from ABB, Siemens, other manufacturers so they can talk for energy management systems? We called it Common Information Model that enables these Lego pieces to connect seamlessly. Then there's a utility communication architecture, UCA, which is similar to the internet, 7 layers, but customized for utility type of work and application. So I proposed, and you can find it online on January 26, 98 to our Research Advisory Council, the EPRI, Department of Defense Complex Interactive Networks. I will cover that. And we extracted 24 technologies out of it, 7 of which in 3 years, we tried to do it every year, but really in total, it was 36 technologies afterwards, post 9/11, when I directed all the security R&D for all the North American utilities, about 94% of all utilities within North America, that we extracted 12 more technologies out of it. It led to, at the time when I presented it, I will share with you what happened, kind of the kind of innovative, disruptive technology, which is from outside, mostly from Department of Defense, what I'd learned the 15 and a half years that I'd worked on those, reaction you get, even if you're gentle and pose it as a really a very clear in every way, but still you get pushback. People said, oh, Dr. Amin, you mean our grid isn't smart? Uh, why do you call it smart grid? So I changed the name to self-healing grid. And then later on, we did an assessment survey by all of our members. We changed the name for a short period to IntelliGrid. And finally, after the 2003 blackout, as Dr. Nunes had in the announcement, smart grid finally took hold. And in the interim, post 2003, US DOE, Department of Energy, had grid-wise a modern grid, and the NIST had smart grid roadmap of $50 million in that area. So this is how it started. 15 years with DOD. I took what I knew when I became head of math and information sciences at EPRI. What can I do for the utilities in America and 44 nations, our international members and beyond? And my childhood dream, having been born in Tabriz, Iran, my parents with medical doctors, Tabriz was going like to Southern Europe, going to Athens or going to parts of Italy. We had good quality of life back then. But if you drove 10, 15 miles outside the city, 1966, 1967, there was no electricity. Villages were agrarian, almost like you are in 1820s in Europe. And one time, my maternal grandfather had founded the Iranian Red Cross and had helped actually many other countries in the region, including India, with Nehru and his famous daughter, Mrs. Gandhi, create a public health system in India. So we arrived in the village too late. They had no electricity, they had no telephony, they still use wells, water from deep wells that were carved by hand. And a lady in her early 30s had passed away during childbirth, and her baby had died. And on the way back, I asked my parents, why don't they have hospital here? And my mother, graduate of both Sorbonne and Cambridge, said, Massoud, it's a lot more basic than that. It's not just medical care. They need electricity. They need clean water. If you have electricity, you have refrigeration, you have lighting, you have a 2-room clinic, you have a 5 or 6 grade school, and it changes life. So they dedicated a lot of their life in partnership with many others to bring that fundamental infrastructures, roads, bridges, electricity, clean water, telephony to poor parts of Iran. So that affected me, even though my natural tendencies are in humanities, social sciences, poetry, literature, biological sciences, like my ancestors have done for about 1500 years in that part of the world. I decided to be an electrical engineer when I was 6 because of that experience. And my first week in the US, July of 1977, was the horrendous New York City blackout. So in one side of the world, going back to my opening message, I saw villages without electricity. On the other side of the world, in New York City, and I'd been to Europe many times, but I saw the city, the biggest, the most powerful city I'd ever been to, in despair. Unrest, looting, many arrests. I mean, the whole social fabric of society collapsed in those 25 hours of outages in New York City. So what I proposed to our members, funders at EPRI was exactly what you're seeing here. And I will show you some of my slides from back then that is on the internet also. You're welcome to look. What it led to, 5 months later, launched the EPRI Department of Defense Complex Interactive Network Systems Initiative. Layers of infrastructure for energy, fuel supply, power, the whole power end-to-end, communication overlay, markets, a little bit of environmental emissions impact, CO2, NOx, and sulfur oxide, but mostly also on reliability, efficiency, resiliency, market, energy markets, and the whole thing. Basically, system of systems with connectivities, dynamical systems, but like a system of systems with actual data that utilities, our members, provided us. And we shared the non-sensitive in over 4,000 publications, and I summarize them every year in a report, annual report, about 200 pages. And the final report is 160 pages, again, is online. What we did within this initiative. 108 professors, over 240 graduate students. This was my actual presentation on that January 27th, 1998 day. That what is smart grid? And they had told me beforehand, don't just call it smart grid, call it something else. So I kind of put that, but then I changed it afterwards to self-healing grid in about 2 days later. Basically, the overlay of computer communication automation technologies that operate as an overlay in parallel with the grid, similar to C4I systems that I had worked on for about 15 years. Command, computers, communication, control. C4I is, having intelligence, actionable intelligence. So you have used this before. Situational awareness early on to do proactive measures is fundamental. And as Peter Drucker said, you manage what you measure, which I agree with. And knowing what to measure, measuring it would give you a major advantage. I would also add to it, and I've said this for about 28 years, if you price it, if you value it, you manage it even better. That's why value of this and price of it, economic aspects and so on, and the whole emissions, everything matters. So those, from that point, even back then, I called it microgrids. We used to call it local area grids, but the 5 drivers why we need to do this are on the bottom of the screen. Why we need self-healing? Because I had seen what outages have in California, had a major outage that could have been prevented. And actually, we developed that technology. It happened in 1996, 97. Economic impact, $1.5 billion of that outage because a tree attacked a line between Oregon and California. Actually, it was too much was going through the line. It was a hot summer, August day. We were bringing hydropower down. So the line was overheated, sagged into a tree, and tree trimming budgets were reduced to improve the cost savings, etc. And it was a wet winter. So the combination of factors, single event led to other dominoes falling, cascading event. Also security, and doing this with real careful engineering design with security built in as a design criteria rather than glued on, patched on as an afterthought, as we do every day in our PCs and our laptops and so on. So there were 5 pillars that I shared with them. This proactive look ahead simulation, fast isolation of crown jewels areas, hospitals, emergency services, etc., or population centers, and then adaptive islanding, and then restoration. This it really is that really, when you think about it, is definition of resilience. And resilience enables robustness. I won't go too much into it, but I had been to countries, Eastern Europe, elsewhere, that they built 50%, 70% larger equipments that could handle frequency changes, fluctuations, oscillations in the system, because the system couldn't be smoother, more better managed, controlled, or smarter. Instead, they built it in the end use by putting a lot more in that, and you would see lights flickering all the time. So that's an option, but if you build it this way, you can also make the components more efficient, most cost effective, less footprint on the environment and on manufacturing sector. So in a nutshell, smart sensors, secure communication and analytics increase, and also instead of one-way flow, Kirchhoff voltage loss, current loss, you make the system more controllable into a switch network with power electronics, DCs, and so on, and secure it. And that's the overlay right there. Overlay over all of them. I'm not showing you generation, supply chains, but all of that. You get basically a huge dashboard, and depending on where the risks are displayed, you zoom in, boom, you go, what is it? Is it a one substation in LA? Is it a major weather front that came? Is it an equipment, a transformer that you're doing analysis on its fluids is about to fail, and you can send the crews before it fails to change it. So I'm pleased that after about 9 years, it passed, became the law of the land in the United States. And here's the actual wording from the law 22 years after 2003 blackout, back in 2007. So please check out the blue sites. Look at the beauty of words that you would expect an attorney or attorneys mostly to finally proofread and accept this. Increase use of digital information control technology to improve reliability, security, and efficiency of the grid. Dynamic optimization of grid operations and resources with full cybersecurity. Exactly that. That's what we have been trying to do since January of '98, and we're still on our way. So to get into nuts and bolts of it, I hope this context made sense. We are done with the context. So to move forward, our traditional grids kind of review what we talked about. They lack situational awareness in the level we need. SCADA systems measure every 2 to 4 seconds. PM use phaser measurement, sensors with satellite time stamping, transistors. They do it much faster, 30 to 60 times a second. US, Brazil, China, other nations have deployed that, and we need more of that to get better situational awareness. One of my colleagues used to say the old version SCADA is more like taking an X-ray every 2 to 4 seconds. MRI is more like the PM phaser measurement units that you get high resolution colored, you can go in, you are faster. Also, electrons travel so fast, almost at the speed of light. If electrons had zero mass, they would become photons. So, and also the fact that the system follows Kirchhoff voltage laws, current laws, electrons flow in the path of least resistance, not like a telephone network or supply chain that you can switch it, you can command it to go down this particular line. So you have to take action within 3 or 4 cycles quickly to avoid outages. So back then, we didn't call it AI, but we used a lot of verifiable, provable neural nets, what we call verifiable AI, expert systems, data analytics, stochastic optimization control, sensors, etc., into it. And also microgrids, local area grids to support local and use local resources, renewable storage controls to make it seamless integration, and the market adoption. So predictive maintenance is huge. It already views both the digital twins as well as better analytics, better foresight to detect issues early on. Self-healing systems, we have applications within microgrids that have been implemented in communication systems more so. So the 3 big bullets in this one are the 3 you're seeing here. that are already implemented, not just pilots, but we need to do a lot more of that at a larger regional scale, city scales, and national scales. This is from, my goodness, almost 18 years ago. After 2003 blackout, I was interviewed and wrote an article with the head of Phil Shui. He's a physicist and he was the science writer. We wrote an article for Scientific, basically American, showing how 2003 blackout could have been prevented. And we used my methods, my models, and what I had learned thanks to the large initiative. If we had used our technology, we could have avoided that within less than a second, basically. Within 0.6 of a second, we could have avoided it. And here are kind of displays of what the simulation, what the assessment based on real data shows you how it would have been avoided. So combination of three things are coming. This is already here. Question is scaling. Microgrids, local generation storage, either isolated in isolated parts, but more so connected to the grid seamlessly. Renewables such as wind, solar, geothermal, depending on the benefits and economic impacts and resilience, combined with storage systems. Real-time monitoring and control. So these three are huge, and that's part of what we are doing here. So you're retrofitting the old system that is usually what most of us have with these local area microgrids and combining them with smarter, more resilient, but security again built in. By digitization, if we don't do it carefully, we introduce many vulnerabilities. So more on the local level, at another interview by Nature about 17 years ago, I drew a map of what it would be for a city, what this microgrid would look like. I took a screenshot of it with my first iPhone. I took a picture of my white screen, white board, sent it to them, and they did a great job, much better than I could draw. So every building becomes an efficient, reliable energy node. And depending on whether you're running a massive data center or you're running an office or residential, the mix is really different of what you need, what demands you need. But the overlays here, what a city would look like, and we are already doing this actually. Here in Minnesota, we have 3 cities who are run similar to this, not quite as fancy. Throughout the world, you can see what are the microgrids and smart grid for smart cities, basically. This enables smart cities, is the underpinning for smart cities. So how about infrastructure interdependencies and risks? These are the 16 critical infrastructures according to the US Department of Homeland Security. The ones that are bolded are the ones that we have in our model, in our assessments and deployments. We include other ones. How can we improve healthcare delivery as part of smart society, smart city, etc. But those are more assessments we do rather than the foundational equations and data that we integrate. And this is something else that I presented once, I believe, at IAMOT a long time ago, called global transition dynamics, the system of systems, dynamical systems, that you can look it up, that I apply in this area. And my company is founded on this. Exactly same principle at Energy Policy and Security EPS Associates. So these are the interdependencies. And here I'm showing you qualitatively, but those interdependencies are on power, on electricity. I give you a second to check that out as I toast you with coffee. So think of this as physics, dynamics, or markets, or discrete events, things that occur, either predictable, planned market changes, etc., that you're doing, or they're done, they just hit your system, what we call discrete event dynamical system. Here's a more detailed version of what those interdependencies are. Bidirectional interdependency, we put physics, chemistry, price, markets, emissions in all of them. So each node basically has its own dynamics, has its own stochastic, has its own prediction ability, and we use everything that we learned in grad school and more into these. This is actually a diagram that we use to do assessment, policy assessment, risk assessment, and so on. You can click on it and it goes to a system of nonlinear PDEs or a bunch of discrete equations within our systems. I won't get into it. I have a paper that I may share with you. A lot of it is proprietary, but I'm happy to share any details that you're interested in. This has been my life's journey, really, in different ways, specifically since 2003, but more so since 1982, what I've worked on to make this dynamical system real, pragmatic, and applications to society, policy, investments from macro to micro level. And these are the layers that we include in there. The holistic, not just the 7 layers we had, but application layers within that. Grid data sharing, agile communication network, self-healing network within that communication, and better connected, secure, smart terminals. This I already shared with you. So breakdown of what happens in this area is getting to the last part of my presentation, investment requirements. Globally, these are some of the high voltage on the transmission side, 15K and lower on the lower side, on the right-hand side. I'm sharing with you the data. In a nutshell, it's, as you may know, depending on the nation, depending on the region. In the US, our biggest challenges typically is investment policy and regulation. That depending on who is in office, either they deregulate, create a major shift, chaos, or they want to regulate, and that creates another, and as you know, uncertainty. And then trying as engineers or as analysts to assess them, you can do all your best. California energy crisis. My team and I, we predicted it 14 months before it happened, presented it to California Energy Commission, to other stakeholders, and you said, Dr. Amin, and that was my team. You're right, but we're stuck. We have already done this. We don't know what to. We shared with them. We couldn't do policy recommendation because EPRI is a non-profit. You cannot do advocacy. It's a 501c3. But we did policy assessment, showing them exactly what to do in terms of engineering to improve so the system would work. But they couldn't. A year after that, they gave us the highest awards to my team, total of 6 of us and me, for having analytical capability to understand couplings between markets, system, and policy. Too late. We almost turned the award down because we said, look, you guys created pain in the society that we told you 14 months before. And you all nodded, said, yes, Dr. Amin, you're right, but what do we do about it? But anyway, these are things that we have done, we can do, we are doing right now. We have 64% of outages come from the local system. That's why you're seeing a lot of emphasis in microgrids and local augmentation rather than the big wires. We're focusing on local wires. And AI is huge, about 30% reduction in equipment failure, transformers, switchgear, etc. Automated grid management, it's really amazing. About 25%, I'm being very careful here on the verifiable, valid data that we have. And we have, my goodness, we run typically in the order of 700,000-800,000 simulations to assess them, and then we validate them with real data. And then we go apply it, almost like a combat pilot. We do it beforehand, wind tunnel testing with high fidelity, all kinds of stuff. Then we actually fly it. And then we do pilot studies, and then we implement it within the communities. And some of it, we are also doing hands-on in poor parts of state that I live in. And we are also doing job training, retraining, and certification for these, not so much high tech, but solar panels, wind, storage, and controls. And we train people who actually get great jobs in poor parts of Twin Cities near me. And I'm the Chief Technology Officer at Renewable Energy Partners. And I have been doing that pro bono for 8 years, but more so since I have less on my plate. more so full-time in addition to my job in DC. I do this since August of 2024. So I'm at your service for that also. Local microgrids, solar, small wind, storage, smart controls, and automation. And these are just to share with you the more bigger picture of what I have done in this area. So in this transition, there are many challenges, and Breno has done some really excellent related work that I look forward to hearing more about. I read his papers that can really help big time in this area. You have policy, supply chain, grid congestion, and then you have the other three. So to create a balance is often futile. You have to make those local changes customized with the architecture, which is proven, but you got to focus on these factors and do what we talked about earlier. How do you build resilience? So resilience is faster recovery, faster restoration. First is if you can minimize losses, you can actually have that proactive security and resilience to focus on how to save most of the system, like what we have done in many areas from the 2003 blackout and even before that and after that, you can save a lot. So first is reduce the depth of what that resilience trapezoid is and reduce the duration of it. Make it less impactful when it hits, or multi-factor 6, 7, 8 hit, and then restore it faster and make the system stronger, smarter from that loss. It's almost like martial artists that, yes, you may lose some, but you become better because of that. You have learned from it. And you anticipate, you look, but you're not too nervous. You don't react to everything because that would create instability in the system, too much fluctuation. So the good news is battery costs have been down about 90% almost now, and solar costs are down about 70% since about 15 years ago. And federal state incentives that came out of infrastructure investment and jobs acts. And by the way, not to talk about politics, red states in the US have benefited by far a lot more from these jobs than the blue states. And I'm non-partisan, but I can tell you that this is good. Electrons are not red, electrons are not blue. We need them, we all need them, and it's good for our society, national security, job security, and environmental security. So bringing back the outages, this is the urgent need for resilience, shorter duration and less impact. So when we are hit hard, we try to I believe the wonderful wisdom we have in many cultures, including in Christianity, when you're slapped, you turn the other cheek, is absorbing that force. And I've taught that principle in my other job, 58 years of martial arts, or 56 years of martial arts in my 63 years of life. You go with the flow to absorb so that you don't absorb all that shock. So there are ways to make our system much more flexible, much more adaptive to absorb these shocks, but we need that smart and flexibility in the system. And that's what microgrids and smart grids enable you to do. So we use metrics for resilience that are very detailed, but here is a summary of them. The direct metrics in terms of impacts and indirect ones. The direct ones are the four you're seeing on the top, and the indirect ones are the critical services without power, what we talked about earlier: fire station, emergency response, police, hospitals, mayor's office, first responders, and so on. And then you do also dynamic risk assessment in a proactive way on the key assets in your system. This is all connected together. And I have had the privilege of helping others in Department of Defense. Here's a non-classified version of it for resilience, that each of these basically enables you to avoid, prepare for, minimize, adapt, and recover faster for anticipated or unanticipated shocks in your system, to make sure that your operational excellence and resiliency meets mission objectives in a nutshell. And you see the things, the components we include. And you can see how old the screen is, so I'm not permitted to share anything more new than what we have done in the past. Yeah, we do the physics, as you see. We include also financial models and so on within that. California, you saw, unfortunately, the shock to the system, what happened. And good news is out of that, the areas that had microgrids uh, saved their society, saved their uh, community, because also they could get water and so on. So there are lessons in terms of loss of life. I won't talk to get to the last part too much about in depth about microgrid, but I think within IAMOT we can do more in this area. By the way, I don't invest or I don't make any money in areas that I work on. Intentionally, to have a clear conscience, to have non-conflict, I have no investments in the areas that I created, interestingly. Even the work I do is, I've been doing is at no pay. So, so I'm pleased to report that I'm not recommending them for self-interest. I'm recommending them to get the mission that I believed in place. For microgrids, in a nutshell, I show you this one. I'm grateful to Honeywell colleagues. They helped a lot in make this happen way back when we were looking at how we do it. I've updated that model. So you have the supply side, which you're seeing. You have utility side, buying and selling electricity. And then you have the, sorry, you have the components, control systems, and then you have the uses you have for it, and then you have all the demand side of it. Not too far from me, OATI, which works in this smart grid, microgrid domain, has a new building. They built it during COVID, opened it right after COVID, about 10 miles, 15 kilometers from where I am currently, which is smart building. It says power back to Excel Energy, our local utility. It has all these systems I talked about. So check out, please, online, what does OATI building look like. Puerto Rico, I briefly alluded to it. Hurricane Maria devastated it during September of 2017. In 2021, 2022, early 2023, when it was hit with a similar storm, we had put microgrids in there. I'm pleased to report that the microgrids brought over 92% of electricity back within 2 days. Maria had created outages that for 8 months, 95% of island finally got power, and the devastation was horrible, beyond anything I can say. Microgrid, we have one of my former students, Colonel Matt Vatter, did a great capstone with me at University of Minnesota. He was the head of the strategic planning at Minnesota National Guard. By the way, they are the largest deployed National Guard force globally in the last 20 years. They're amazing people. They're also humble, a lot of engineers who work there. So he developed this microgrid in a place that's about 50 kilometers from where I am right now. And it keeps the base up. These are examples of some things I had the privilege of helping with when I was at another company in North Carolina, what experiences we have with microgrids and electric transportation, energy storage, and with Luma Energy back in Puerto Rico. So outlook, to wrap it up. We hear about critical rare earth minerals, critical materials, is key materials actually in this area. Lithium, copper. In the US, we have huge reserves of it, but we don't mine it. We instead buy about 70% of what we buy is from China. Labor shortages, skilled labor, and that's why locally we have created that, and it's transferable to other nations. I'm at your service. If you're interested, we can partner. We don't make money on it. It's a service we do. It's a non-profit. To retool, retrain hands-on people. And I've done that through IEEE in the past in Smart Village on rural electrification. But we can do what we do as renewable energy partners to support you. Founder of it is my dear friend, my brother, Mr. Jemez Staples. He grew up in that neighborhood where our headquarters are. and he is highly regarded within the community. He's African American, has seen what it is, and he's amazing. I mean, the reason I do it is because I believe in it. Secondly, is because of him. So I highly recommend, if you're interested, check out our website. Again, we are not rich. We don't put the money into the website. So the website may look older, but Renewable Energy Partners is a good place to check it out. And we'll be happy to help you with retooling, retraining, and so on. And policy risk. So on the other side, demand, huge demand. Data centers are a big part. They double every 7 years or so, depending on the economy and digitization. I can get into it. How much does one tweet take? How much all the billions of tweets take? They take, basically, in a nutshell, 5 to 7 large coal plants just to run X, formerly Twitter, a year. Think about it. Just, I mean, we pick up our smartphones, we pick up our smart devices, and we say, but it somewhere collective impact comes from a place. So the more digitization we do, and we feel, oh, I have an electric car, congratulations. But what's the impact of that on the system? It's better than the alternative, but there is impact collectively on the scale of these things are getting or may get deployed. So this is a foresight rather than scaring anybody. We got to take action. That's the key message. Grid readiness are not optimized to handle this. Investors, absolutely. It's a need all the way from solar, which is not enough, wind, but also you see small modular reactors for large data centers up to 300 megawatts that they can provide. And they're fail-safe, Gen 4 reactors that France is using and others. So much more severe, more frequent. Modernizing the grid with these is a fundamental part, is crucial to do. And if you do it, I have had the privilege of working with many. This is the summary that I prepared for you to summarize all this. Predictive self-healing metrics. We use same metrics, but on the right hand of the screen, you see each one of them clearly articulated. If I present at IAMOT in 2025, I will update this, share some of this with you, and map it to exactly what parts we can do, what areas we need. We don't need just engineers. We need people who can do all the areas that you saw. I won't get too much into it, but we need a bigger tent. And I believe that in IAMOT and similar organizations, we got to get and collaborate together, get resources for faculty, graduate student, companies to collaborate together to make this real. Because in engineering, we typically go deep into one component, one device. We need more people who are more interested in both the system and then the areas within that we can go and the coupling between them. So these are the other parts that we use. I've had the privilege of briefing on this, but these are up-to-date data as of just Monday this week of what I put together in this presentation. And I presented a shorter version of it. We had a meeting with within the research and development between University of Minnesota community, and national security experts Monday of last week, which I shared a different version of it in this area. So water nexus is huge. I talked about electric power and water in villages near where I grew up. And this is huge for us. And you have read books like Water Wars and so on all over the world. But that's a huge part that we need to address. And this, for our part of the world, is management, transition, technological leadership, and the science engineering behind it. So what has happened recently since the election? These are showing you some of the 4 nuggets where we are. Smart grid market growth is huge area, and it's growing fast, and it's practical. It's no longer trying to convince the utilities in January of '98. Now it has taken hold. I'm very grateful, happy to see the effort by many leadership globally in this area. Nuclear has come back, small modular or Gen 4. You're seeing it on the lower left-hand side. Storage is expanding, not at the rate that we should, And then renewable has challenges, mainly because of supply chain constraints, intermittency issues, but storage can help that. And then policy should be supportive of that transition. And in many parts, local or national policy is not conducive, or they overdo it. Then it backlash, the hype dies, and then they have to do that. Since the election, this is what has happened in the US, bring you up to date. Fossil fuel offshore drilling, basically in what I have heard confidentially, anything that has a word climate in it is taboo. So don't use the word climate if you're talking to certain powerful colleagues. Fossil fuels are back, drilling project expanded on federal lands, renewables, IRA subsidies are under review, but the fact that it's supporting constituents of red states, and the way it works basically is constituents email doesn't do much. You got to call your senator or congressman to make an impact. They track metrics that my Peter Drucker's is calls you place or town hall meetings you go to, not so much the email or signatures, etc. That doesn't make a difference. So advocacy, but advocacy based on truth and ethics and integrity. Nuclear, increased support for small modular reactors. So these are the three takeaways in the last 6.5 weeks, and we anticipated that. Globally, good news, we have China that leads that. Also, we have UHV, ultra high voltage, by necessity. Again, this is not fear mongering. A lot of folks say, oh, who controls power controls the world, a famous quote by Tesla. No, it's, if you ever really go to China, study deep, I mean, you have so much challenge there. It's a necessity to bring power from large resources to population centers, similar to the, transition we went through, a map you saw in the beginning. Middle East, UAE, but Middle East, there are more fundamental issues that need, that safety, security is needed, but you have the UAE and the Gulf states, as well as Saudi Arabia, others that are moving more and more in nuclear expertise, and Iran, of course. They need it, all of them they need, but I would say small modular for high tech, and then they have a lot of natural gas. I would probably use natural gas extensively because it's less, not good, it has still many emissions, it's better than coal, but and oil, but not as good as it should be. Europe, offshore battery storage, Europe has done a great job. Europe, Japan, they have done a fantastic, Singapore have done a fantastic job in this area. Policy recommendation, increase PPP, policy stability for investment, also for real sustained leadership. We need long-term tax incentive. Take some of the tax incentives in fossil fuels, move those same hundreds of billions into this area, a part of it, not all, because we need a ship with a small trim tap, adjust course and get there, but don't wait too long because climate change, climate weirding is real, and permitting rights of way and so on. So in conclusion, to wrap up my last 3 slides, thank you for your patience. I'm going over, it will be a combination of hybrid grid. Some areas that have a clean slate, they can do this smart microgrid campuses for industrial, commercial residential parks. That can be done. But if you have retrofit, this is some of the areas we're going to see hybrid. Data driven with security. Don't be surprised if many companies don't put security, and government or other enforcement agencies force them to put security, because it's always an added cost or lack of expertise in that area. Investments, especially I would say for large data, stochastic statistical methods, but verifiable AI. If you're going to have physics or differential equations or chemistry in there, we need verifiable AI that we already have. That's actually what we use in my organization. Storage, communication, more and more interdependency, a mega infrastructure between communication and power and energy has already converged. It's getting more and more, the more data, sensor stuff. So it's time for us to make this even larger, to scale it up. It's real. Can we win it? Yes. Is it worth it? Yes. So the real win worth, the answer to all 12 questions is yes. The question is speed and focus and scaling it up. So takeaways, the very last couple of thoughts. It's the largest investment opportunity, the data you saw, but it underpins everything we do in our society. Smart grids, energy spend, and a subset of smart grids, microgrids at a micro level, is exactly that. Nuclear, especially Gen 4 and SMRs, are the player in there. Verifiable AI, cybersecurity are going to help a lot, have already helped a lot. Investors would balance across technologies and time horizons. Thank you for the privilege to speak to you today, and I look forward to your leadership and any questions that you may have. I'm at your service. This is my email at the company, but also my email at the University of Minnesota, which is shorter, my last name at umn.edu, and that's my cell phone. Thank you very much. And on behalf of my university, University of Minnesota, I'm grateful for this opportunity.
So thank you very much. That was a very comprehensive view, and then it does show, the wealth of knowledge and effort and leadership that takes to be a pioneer of such an important concept, and on how to bring these theoretical concepts into practice as well. We have a few questions on the chat, but I want uh, to ask you the first question, if I may. Because we have in our audience here, we have people from very different stages of their career. So I will take a little bit out of the context of the technical side of the context, and I want to explore with you what was the great difficulty that you had in bringing up these concepts to life, because you led a group of 108 professors that supervised 240 graduate students, in multi-million dollar projects. I mean, what was the most difficult part in managing that?
Ironically, thank you for that question. Thank you, Breno. I was asked to give a keynote on this in 2000 and then on a panel in 2001. I've written about it and it's on the web. If you please, if I may suggest, because I give you the quick answer, the website that they have for me at the University of Minnesota, if you just look at that website, I believe it has a tab on the top called research. Go to push on the tab for research, go under publications. At the very bottom of it, that's a great question. You see the publications. At the bottom of that publications is technological leadership, because it underpins everything else. And the very last one on that page is development and leadership of research consortia, lessons learned, something like that. But it's from Vancouver, British Columbia. It was a panel. I'd given a keynote at another conference the year before of what it takes to make it work. In a nutshell, I can tell you that first, I mean, what it is you have an opportunity to think. If you're given an opportunity, even if you aren't, you have that tiny bit, you have a way to help other people get encouraged, get motivated in something that matters. That's something that makes a difference. You cannot pass that up. And that carries you through the storm. Knowing it, not just belief, having every evidence. And as many people within decision sciences would tell, don't act before you have about 40% information, and act between 40% to about 70%, and then don't wait until you have 70%. It's too late, or more than that. So once you know what really matters, what really makes sense, but articulated everything we teach in communication, in making a pitch, and be real, be humble, be modest. Think about it, what it is, and find out all the things. In Department of Defense, we use something called quad chart, QUAD. When you are presenting to the top brass, Make it really in that format. What's the pain you are trying to relieve? How are you going to do it? What's the current state? What are the resources you need? Or use the business model canvas, but be pragmatic, not theoretical. And then start, test your idea in trusted group. Don't fall in love with your own idea. Test it, but don't be discouraged. Every time you hear a no, etc., listen to it. Don't oppose it. Absorb it. Be humble. Bring it in. I can talk about this a lot if you're interested. I hate to put a pitch for my book. I talk about this in a much more clear, pragmatic way, not about my own journey, but I show you the tools you use to get to that decision and then how to execute it. But for now, please look at that summary paper on development and leadership of R&D consortia. I may have it actually. Well, I won't bother you because I'm running over.
No,
Please.
I'm sure we can find a link to that, and then we can put on the communications of IAMOT. I mean, I hope that everyone has signed up to the IAMOT webpage and are getting the newsletter, so we can put it there. No, thank you very much. That's amazing, because I must review a bit of a conversation we had even before this, because I suggested first this to be the 20th anniversary of this smart grid concept, looking at the 2000 the 2000 paper that you had published, and 2005 paper that you published, and then you correctly said, no, look, this is not 2005. There was 7 years before that, so there is a lot of things that we don't see that are in the background in order to reach to where you are. That's
Renaud,
great.
if I may,
Yeah.
that's another lesson I've learned. You do a lot of, it's like the iceberg picture you have seen. You do a lot of hard work for years in silence, in quiet, or in different areas. And then you get an opportunity to run in a mega marathon. Are you prepared to run with humility, with tenacity, with commitment, with strong professional will, but humility in that marathon? That's a huge lesson. I had already worked, imagine that, for 15 years in damage adaptive combat systems, logistic networks, and then to sell it, to get it funded within EPRI, and then convince Department of Defense to do it. I didn't go to Department of Energy because Department of Energy would be more interested in doing it with national labs and so on, which I love them. I funded national labs, but I knew who really cares about technology being brought to the society. In the US, in my humble view, is Department of Defense. DARPA, IARPA, intelligence agencies like that. So it's a whole life form, ecology, if you will. So anyway.
Absolutely. So let's go through the questions here now. We have 3 questions on the chat box. First one from Michel Lejour. Hybrid microgrids tend to seek autonomy from the grid by minimizing the electricity inflows and outflows. Why are we not exploring more collaborative systems where utility grids are specialized on predictable demand, for example, base load, and more unpredictable demand is handled locally by microgrids? That's a great question.
Thank you,
Michelle, feel
Michel.
free to open your mic if you want
Thank you,
to.
Michel. Michel, I will answer it, and please, exactly as Professor Nunes said, basically it depends how you build a microgrid. It doesn't, the premise of seeking autonomy, that's not actually the case. Depends who has designed it, what is the goal in mind. If you want to run, let's say you're running a Department of Defense base, right? We have over 3,000 bases all over the world. Guess what it was before microgrids? It depended on local utility from outside. So they had put either diesel, backup, natural gas, other sources for critical loads. That microgrid during attacks, yes, you want autonomy from the grid. Or some folks that want to live in a remote cabin don't have a grid, so they are autonomous. But the premise of your question, it doesn't describe really the whole picture. The whole picture is, it's not really, it is a collaborative system. Everything I showed you, everything I shared, it's actually bi-directional flow between the grid and the microgrid. Make sense?
Yeah, it makes sense. Just let me slightly rephrase my question. when you talked about a smart grid, you sort of equated it with that idea that it's a self-repairing grid. So it means it detects there's a problem with the distribution network, and then you coordinate some sort of response from the multiple parts of the grid to avoid that problem from creating like an interruption of supply or something like this. Now, but do you think, my question was, is there a way that we could change the design of the microgrid so that we prevent these problems from happening in the first place?
Absolute, great question. Very wise. Absolute. And that's exactly what we do. That's precisely what
Excellent.
we do.
Okay.
I give you a very quick example. One of my students, and this is to give you a sense of history. Dr. Sarah Mullen did her doctorate with me at the University of Minnesota, finished in 2007. Her before this became sexy, she finished in 2007, but we started working in May of 2003. Her doctoral dissertation, major part of it was, what if several buildings, hands-on, there was a theoretical part, simulation part, etc. What if several major buildings in Twin Cities area in Minnesota are smart buildings like the one I showed you on they are smart microgrids? How does it impact the system? That was one. Actually, that was it. How can they together support power, reactive power, not just markets, but from stability, resilience of the system? How about during emergencies? Can it be a shelter for people who need help and have reliable electricity? The other part was, what if out of 2 million cars, 200,000 of them are plug-in electric? Would that help support reactive power and power in those nodes and other nodes, the system? The answer was how to do it, how to optimize it from engineering. The answer is yes. For the microgrids I do for the poor parts of Minneapolis as renewable energy partners, that's exactly what we do. It connects to the grid, it supports the grid. That's why utilities like it. And a lot of our requirements are to assure exactly that capability. Thank you for your excellent questions. Excellent.
Thank you for the answer. Cheers.
Merci beaucoup.
Great to see you, Michelle, and thanks for this really good question. We move now to Saida from Malaysia. For a developing country like us, is it possible to have an efficient microgrid system like yours? Thank you. So any
Saida,
applications in developing countries?
Oh, absolutely, Saida. I briefly alluded to it. Guess where we are doing this? In Minnesota, the poorest part of Minneapolis. And guess what we have done? IEEE Smart Village. We can absolutely do it. And this is the way to go because it's a local investment. It's investment in your community. The cost is a lot less. And we train people right there, hands-on, to run it themselves, to own it, to operate it. This is, in my view, the way to, if I could do this for Africa, Egypt is amazing. I love Egypt. I mean, if I ever would live in a country, I can tell you, US, Iran, Egypt, maybe India. Those are my favorite parts of the world personally to live in. Egypt has amazing resources. South Africa has amazing resources. But to create an African grid, that has been my dream since my teenage years, is very hard, impossible. Guess what we want to do in Africa? Local microgrids, precisely for that reason.
And if I may comment on that, I think the developing countries are a very fertile place for us to think of these solutions because of what is said in the beginning of your talk, Massoud. The cost of having energy can be high, but the cost of not having energy is much higher because you lack clean water, you lack education, you lack health. The knock-on impact on the other valuable things, which is what I call sustainability fitness, on how you address the essential needs. You're preventing society to meeting its essential needs because the energy supply is not there, or it's not affordable, it's not controllable. Yeah. So I do think that it's a very good place to apply some of these concepts and develop them in practice. Victor Chang, Professor Victor Chang, a colleague here at Astra University, is asking, you always like to show a number of new technologies used.
Yeah.
Victor, you're there.
Next door to
please
you.
ask the question yourself.
Yeah,
Introduce
I'm next
yourself.
door to you. I'm listening all the time. Yeah, I'm professor of business analytics. I'm using technology. Although I have an MBA, but people seem to think I'm better with technology. I'm working with technology for a long time. So I saw that your slides with a lot of big words like big data, SDN, IoT, cloud computing, and I used to have students from Germany. They also do the wind turbine, and like they've done like on their end, they don't have to climb up. They just see and then the wind turbine would. But now everybody is talking about AI everywhere. Like you heard about it all the time. So I would like to know your vision on AI and whether your company has used AI or what sort of extent you are going to use AI. Thank you.
Thank you so much for your excellent question. Yes, hype, Gartner's hype cycle, since you are in the business school, hype is not a good thing. So please check out my post about technological hype. It's on LinkedIn. I put a couple of posts in it. I talk about exactly the question that you asked and more. So yes, AI has been around since 1940s in different forms. I personally and my team, we have used it. Even my doctoral dissertation was on combat prediction of air combat, but we applied it, not just concept, but application. So AI currently, and I've given talks on that. I don't know how much I should get into it. So the bottom line is this. Don't follow the hype. Dig into what's there. Large language models predicting the next word, writing the next word are good, but that's not what we need in the areas I talked about. What we use, I said that 3 times. We use verifiable AI. We have been using verifiable AI since 1988. Expert systems with first order logic, second order logic, predicate calculus, that you have consistency of decision making, consistency with data, that basically goes deeper than just rules to make a soup. Goes through the chemistry of the what's within the soup. So yes, the answer is yes, but depends whether it is deep or it is just words and hype.
Okay, yes, yes. Yeah, it's been a long time. Yeah. But because this day, the rise of large language models, generative AI makes it possible. So it looks like the speed in which things have moved on a little bit faster than human being thinks.
Basically,
Yeah.
Victor, underpinning technology, what made large language models possible are transformers that you can process stack. We didn't have that before. So when transformers were created about 5 years ago, it made possible to do the same methods that you now see online for neural nets, for other things, but we couldn't run them in the same way. So I can talk about it offline, but seriously, that's not really an invention that came out of nowhere. You can actually track it from a kind of technology S-curve as well as, and I have that. I'd be happy. Actually, if you like, I don't want to change screens. I gave a keynote on quantum computing 10 days ago. I talked about exactly that area. And there was another fantastic presenter originally from Hong Kong, grew up in Singapore, Dr. Sophia, forgot her last name. She did a great job on the linkages between how these transformers totally transformed the way we use AI. So OpenAI basically used transformer, not transformer, the puppets on the movies, but actual ability to process the stacks of data and information.
Okay. In terms of microgrids, there are challenges. There can be the time if you're using renewable energy, like solar or because you can have excessive power storage, and then you need to store the excessive energy, and then you want to use them back when at night. So in the daytime you store as much as you can, and in the nighttime you then release those storage. What happened was that the storage rate is not very good, because you may retain it depends on what technology you use. We only retain, I might be wrong, but maybe like 60 to 80%, you will consider a blessing, because a lot of energy is very hard. You can get a load, especially in solar, like wind power, and then in the nighttime, because people have to use more electricity, and that's one of the challenge that even without AI, or you have all existing techniques, even like you use nuclear or whatever, it's one of the challenge. I would like to know your point of view, because if we are not resolving the storage issue, it's like, one of the problem you have is the electric car. You can never drive to another city, because if you have problem, on the way back, it will be problematic. So I think storage is very important, because some of the battery manufactured by China, if you put them in, it's very easy to get into fire. So storage is also a very challenging thing, in my opinion. I would like to know your point of view.
So your question, if I may make it into a more direct question, is impact of storage for reliability when you integrate renewables into the system.
Yes.
Okay.
Yes.
So allow me to switch. I show you a practical example that just the most recent one we have done. Entire screen window. Here we go. I will show you this screen. So your question is broad, but it's very straightforward. Basically, in a nutshell, you actually look at, here is just what I did, and this is my memo to my colleagues. Here is doing for a village. This is for a village and for a nation, the whole nation. I won't name the name of the nation, but let's say it's in Africa. Depends how much backup you want. So your question really is, can storage provide that during off-peak, during times that you don't have electricity? And then what is the duration? Most applications, please ask all your questions and I will be happy to answer them.
Okay.
I don't know how much time you have, but I have to leave in about 10 minutes. And I wanted to answer all questions before I leave. So the second part is how many hours? Most applications, they look for 4 to 6 hours of backup, 4 to 6 at a particular level. So that's beyond that. But regarding your question, here is the one: original cost, updated cost, depending on whether you want 12 hours or you want less than that. And then when you go deeper into it, here we go. Here is my summary for you.
Okay, interesting. Maybe in another time, I would love to talk to you in the other separate meeting.
Yes.
Thank you so much.
This is really to show
Thanks a lot.
Yeah, it connects to the other colleague's question.
Yeah, thank you.
We have other questions here in the chat. So I think if we had more time, we certainly could jump in the discussion and also look at the advancements of hydrogen that are happening to place as well, that are a different form of storage of energy. But let's, Raji, can you be quick on your question, please? Open your mic and your camera if you want, and ask a question. Raji, are you still there?
I'm not asking a question, but I'm going to put something in the chat for everybody to see. Massoud, this is just a drop in the ocean from what my country, Singapore, does. And if you want to talk more, or anybody else, I'm happy to do that. So I'm just going to put this in the chat. For some reason, I don't know whether you get the PDF or not. Did you? Are you seeing the PDF?
No, if you need to press the arrow on the side to make sure that it goes in the chat. So since you don't have a question, Raji, let me go to Muhammad Afzal.
Yeah.
Hi there. My name is Muhammad. I'm from Pakistan. Pakistan experienced major blackout in 2021, highlighting the need for more resilient grid. Based on your work with self-healing grids in the US, what lessons can an underdeveloped country apply to prevent such large-scale failures and modernize its power infrastructure? not very different from
Mohammed,
the
great
COVID one.
question, but that's a whole major undertaking. Interestingly, I followed that outage, I assessed that outage, and I've written about it. Yes, please go ahead. You were going to say something.
No, that's fine. That's fine. Thank you. I'm listening to you.
So the solution for Pakistan, it's gonna, in my view, is exactly what we talked about. A combination of strengthening the backbone, having a better generation, reliable generation, transmission, and then for cities, major cities, to have more efficient. I would remember where we started from, which was efficiency from end use from one end to the other end. Look for areas to reduce load. If you can reduce demand by reducing inefficiencies, that's number one. Number two is then what you retrofit, what you strengthen. Number three is then what areas, what buildings do need backup generation? Or would you create a microgrid from the substation that feeds into it to that whole area for schools, for hospitals, for emergency services, and so on? So it's a major, what you're asking is huge. And it's doable, but it needs actual data, actual people engaged from the utility, from others. I'd be happy to help pro bono. If you're connected, I'd be happy to help at no cost. And I've been invited
Thank
to
you.
go to Pakistan. I've never been to Pakistan. I happen to be from the neighboring country originally, so I would love to help
Yeah.
and come there at my own dime, my own money. Yes, sir.
Thank you so much. Thank you so much. That's why I was asking just for basic thing, not huge, so I get it. And thank you so much for your presentation, and it was really prayer. And thanks a lot.
Thank you. My pleasure, Mohammed. Thank you. Pleased to meet you.
Well, thank you. I think we had a wonderful session here. I must thank again Professor Massoud Amin, the father of smart grids, that you've learned from, how careful you need to be with your words when you're creating something new. So that's why he had to put smart self-healing grids to not upset other people and be diplomatic on the innovation of the work that he was doing. But Massoud, many thanks for delivering this talk. It has been wonderful. I think very informative. It's a real privilege for us in IAMOT and our members to have been able to hear from you, on the technical side of it, on the human side of it, but also on the more technology policy aspects that come along with it and the end-to-end analysis of the energy system. So thank you again, and thank you all for attending this session. I hope you have enjoyed as much as I did.
Thank you, Breno, for your leadership of IAMOT and making this happen. I'm at your service anytime. Colleagues, take good care. Call on Breno as our president at IAMOT, and call on me as your geek, a happy geek on a mission, if I can help you in this area. Thank you.
Thank you very much. I will stop the recording now.